Alright, so today we're doing generalized compressibility, which is 3.11. So this is one of the last chapters that you actually cover in this first part. So that means that we are almost to the exam, right? I know that's probably scary for some people, but we are, yes, almost to the exam. So we're taking a little bit of a break in this chapter from what we've usually been doing, and what we've usually been doing is the properties of like state, finding H and U and quality and saturated tables and whatnot, right? Generalized compressibility is not anything like any of that. It is using the ideal gas law essentially, and it's using critical temperatures, I think, or I can't remember what they call them exactly, but we'll get to it in just a second. So, it says the object of the present section is to gain a better understanding of the relationship among pressure, specific volume, and temperature of gases. This is important not only as a basis for analysis of gases involving gases, but also for the discussions of the second part of the chapter, where the ideal gas model is introduced. The current presentation is conducted in terms of the compressibility factor and begins with the introduction of the universal gas constant. So right here, the compressibility factor in this chapter is Z. And essentially it's going to tell you what this is that it tells you how close to ideal you are. And I know that might seem dumb, but that's what it is. It's going to tell you that. So let's look at this. Universal gas constant R. So let a gas be combined in a cylinder by a piston and the entire assembly held at constant temperature. The piston can be moved to various positions so that a series of equilibrium states at constant temperature can be visited. Suppose the pressure and specific volume are measured at each state and the value of the ratio P, so pressure times specific volume over temperature, V is volume per mole, determined. These ratios can then be plotted versus pressure at constant temperature. The results for several temperatures are sketched in figure 310, which is over to the left. When the ratios are extrapolated to zero pressure, precisely the same limiting value is obtained for each curve. That is, the limit as P goes to zero is P, so P times V over T goes to zero, you get R. So right here is what they're talking about. Essentially, this is what they're doing. They're like changing different, they're changing temperatures, and these are like these lines you're getting, these little curves. So that is what they're talking about in figure 310, I think. Yeah. Then it says where R denotes the common limit for all temperatures. If this procedure were repeated for other gases, it would be found in every instance that the limit of ratio PV over T, as P tends to zero at fixed temperatures, is the same, namely R. Since the same limiting value is exhibited by all gases, R is called the universal gas constant, which we all know what R is. But this is the units for R. So you do have to be careful, though, which ones you use. But these are the very common ones for R. Alright, so now we have the compressibility factor Z. So this is what this part of the chapter is for. And this last part of the chapter is sort of like a closing arguments type thing, is that essentially it's a very small part of the chapter. But generally there is a question on this on the exam, and it's really easy, so fairly good to pay attention to. So it says the dimensionless ratio PVRT is called the compressibility factor and is denoted by Z. So Z is equal to P times specific volume over RT. Okay? So let's hold on to that. It says, as illustrated by subsequent calculations, when values for P, V, R, and T are used in consistent units, Z is unitless. With V, which it's m times v, where m is the atomic or molecular weight. The compressibility factor can be expressed alternatively as z pv. So right here, essentially this right here, one of these is in different units, so you can express it in both. I think this one is the one in per mole, and I think this one's per mass. And then they replaced R with the universal gas constant divided by the molecular mass of the gas. So you get a more specific, you get one that is in terms of mass. So you can do them both ways. And in this class you will, because we actually, in this class, we're concerned with mass. We're not concerned with moles as much. So you'll probably have to do this part right here. But I'm sure in other classes you've done this already. And so this right here, table 3.1, is the table of selected gases, apparently. So you have to go and find this in the back of the book. And I think I can't remember which one it is. Let me see. Maybe it is the first one. Yes, so this is one that you'll use right here, but this isn't the only one, I think. Yeah, actually, this is probably the one you use. So right here, it has all of these different ones. Nitrogen, hydrogen, helium. They give you the molecular weight in kilograms per kilomole, and there's a table like this for the English units as well. And then you have the TC, and then you have PC. So really quickly, we are going to talk about these in a second. These two are the main thing of this chapter that you're going to have to know. So know that they come from the very first table in each table section. It's table A1. So hold on to that. And it says R is a constant for the particular gas whose molecular weight is m. Alternative units are kilojoules per kilogram Kelvin, BTUs per pound Rankine, and feet pound force per pound Rankine. Calculated from equation 3.25. Equation 3.21 can be expressed in terms of the compressibility factor as p tends to 0, or the limit of z as p turns to 0 is 1. That is, the compressibility factor tends to unity as pressure tends to be 0 at a fixed temperature. This can be illustrated by reference to figure 3.11, which is assumingly this, that shows hydrogen plotted versus the pressure at a number of different temperatures. In general, at states of a gas where pressure is small relative critical pressure, Z is approximately 1. So what this is basically saying here, like I'll try and summarize this, is that the closer you are to Z equals 1, the more close to ideal conditions you are. So basically, at this line, hydrogen is a perfectly ideal gas, right? Essentially, is what it's saying. So on this Z equals 1 line, that is what we're looking at. That is essentially ideal gas, right? But outside of that, like when you get Z values that get higher, it's not ideal, right? That's kind of what we're at right now. All right. And it says generalized compressibility data Z chart. So this right here, this is where we introduce these PR and TR values. So hold on to this again. So figure 3.11 gives the compressibility factor for hydrogen versus pressure at specified values of temperature. Similar charts have been prepared for other gases. When these charts are studied, they are found to be qualitatively similar. Further studies show that when coordinates are suitably modified, the curves for several different gases coincide closely when plotted together on the same coordinate axis, and so quantitative similarity can also be achieved. This is referred to as the principle of corresponding states. In one such approach, the compressibility factor Z is plotted versus a dimensionless reduced pressure and reduced temperature, and these are TR and PR respectively, okay? And they show that in the next equation. So, reduced pressure and reduced temperature are simply dividing the actual pressure you have divided by the critical pressure, and where that critical pressure should be, I guess, familiar is that I showed you it here. So TC and PC for selected compounds. This right here is where you have to go to find that value, okay? And so what you would do is, like, let's say we're looking at argon or something, you would go down here, you'd grab TC, grab PC, right? And then you'd go back to your question, and you divide the pressure and the temperature that they actually gave you, and you would get the reduced pressure and the reduced temperature. And so this right here is what you use. These two PR and TR are what you use to graph. So you're not graphing. You're using a table to find Z. Okay. And then it says this results in a generalized compressibility chart on the form Z as a function of PR and TR. So we're going to go look at this in just a second. It says the solid lines denote reducing isotherms represent the best curves fitted to the data. Observe that table A1 provides the critical temperature and the critical pressure for a sampling of substances. So we were just there. So this is what it ends up looking like, right? So this right here is reduced pressure on the bottom, and over here is Z. And I'll actually go to these charts in just a second. But essentially what your goal is to find the reduced pressure, and you want to match it up with your reduced temperature, and then slide over here and find Z for compressibility. So for example, let's just say we had a reduced pressure of 3. And let's say we had a, I don't know, reduced temperature of 1.75, right? I don't know. Like I said, let's get crazy here. 1.75, so we go up, 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 up. So right here is 150. 2 is the next one, so we'd be halfway in between, right? So let's just assume it's like there. That means that you would say that your Z value is like 0.89 or something like that, right? Does everybody see how that worked? One sec, I don't have the speakers on, but if someone talks, now you can probably hear him. But you just understand how this works. Essentially, if once you get these two values, the TR and PR, you can then find Z. Is everybody good with that? That's what you're going to be doing in the questions, essentially. If they ask you something like this is what you'll be doing. You'll be finding Z using PR and TR, okay? And we'll probably do an example here in just a minute as well. Okay. So it says, a generalized chart more suitable for problem solving than Figure 312 is given in Appendix Figs A1, A2, A3. So I'm actually going to go pull those up just to show you, but they're at the very end, if I recall. I have to go find them. Oh, no, they're further in. That's right. They're like all the way at the back. Yeah. So yeah, so you'll be able to use these charts in the exam. So right here is one of them. So this is like this is a more zoomed in version right here, and then this one is further out, right? So this is PRs less than or equal to 10. This is PRs less than or equal to 1, right? And then this is PRs less than or in between 10 and less than 40, okay? And so, like I said, you do the same things. What you're going to do is you're going to find your reduced pressure, right? Using your critical temperature or critical pressure and your critical temperature, you'll find both of these two things. You'll find TR, which are these lines going across, and you'll have your PR, and you'll find where they meet up, and you'll go over and you'll pick out your Z, your compressibility factor, which is right there. So there's a little more to talk about before we do a question on this, but there is one more step right at the very end. So it says, let me see. However, for the stream broke for you. Anyone else? Is it good? So there's no audio. There's never been any audio. But just reload or come into the lecture again. But yeah, there's not any audio. So really quickly, it says it just describes each chart. It says, however, for the 30 gases used in developing the chart, the deviation is at most on the order of 5%, and for most ranges is much less. The value of specific volume are included on the chart, generalized chart, through variable V sub r, called pseudo-reduced specific volume. So this type of thing we don't really talk about very much. If they do ask for it, this is what you're going to do though. So it says the pseudo-reduced specific volume gives a better correlation of the data than does the reduced specific volume. VR is equal to V over VC, where VC is the critical specific volume. Using the critical pressure and critical temperature of a substance of interest, the generalized chart can be entered with various pairs of the variables TR, PR, VR, all these, right? Then so this is VR prime, PR and VR prime, TR and VR prime. It says the merit of the generalized chart for relating P, V, and T for gases is simplicity coupled with accuracy. However, the generalized compressibility chart should not be used as a substitute for PVT data for a given substance as provided by tables or computer software. The chart is mainly useful for obtaining reasonable estimates in the absence of more accurate data. The next example provides an illustration of the use of the generalized compressibility chart. So this is what we're going to do right here. Okay? So we are going to very quickly do something like this and show you what we think, why we are sort of using it. Let me go ahead and get the canvas open. All right. Then we'll size her down here and look. Okay. So let's go ahead and we're going to do, I need to get the text tool real quick. Text tool. All right. So let's do a little bit smaller than that. Okay. So text tool. We're going to do the knowns and unknowns like usual. Okay. So for this question, it says a closed rigid tank filled with water vapor, initially at 20 megapascals, 520 degrees C, is cooled until its temperature reaches 400 C. Using the compressibility chart, determine the specific volume of the water vapor in the initial state, the pressure in megapascals at the final state. Compare the results A and B with the values obtained from the superheated vapor tables in A4. So we're going to find them using the compressibility chart first. Then we're going to do the regular way that we have been doing it. All right, so we have 520C. Right, that's T1. So T1 is equal to 520. P1 is equal to 20 MPa. And then we have T2 is equal to 400 C, right? And we're looking for P2, right? And the specific volume. So looking for the little V2. So that is where we are at currently, okay? So I'll go ahead and click off of that. So this is what we're doing. Let me drag it down a bit. So the first thing that we have to do is we got to grab the relevant information about state 1, right? So I'm fairly certain what they're going to do is they're going to grab, because remember, because it's a closed rigid tank with some amount of water vapor in it, what does that mean for us? That means that volume 1 is equal to volume 2, right? Essentially. Does anybody agree with that? So let me move down here a little bit and show you. I thought I was getting a phone call. Never mind. Alright, so right here, this is what I was talking about. So it says from table A1, TC is 647.3 and PC is 22.09. So we are actually going to go there really fast. So let me go ahead and grab this. Let me see if we can get it. So water. So right here, this is what they went. We had to go grab all the relevant information. And what I mean by relevant information, I mean that we have to go find the molecular weight, or the atomic weight, whatever, the big M, right? We then have to go find TC and PC for water, all right? So I'm going to go do that. So drop it down here. Let's do step 1. So then we had to go find all the things. So we have big M is 18.02, and this is in kilograms per kilomole, right? Then we also had to find that T sub C is equal to 647.3. And then we have, and that is in Kelvin, sorry. P sub C is equal to 220.9, and that is in bar. So that right there is what we had to do. We had to go to table A1 and go grab all the relevant information about our question, okay? So step 1 completed, right? Found all of that. Now, the next part is we have to use these in our question, essentially. And what I mean by that is we need to move on to step 2. So step 2 is to find the reduced pressures, right? And the reduced temperatures. And so if you recall, T sub R is equal to T divided by TC, right? And then P sub R is equal to P divided by PC, right? Everybody recall? These two equations right here is how you find the reduced temperature and the reduced pressure. So we need to find both of those. And so I will go ahead and insert these into the question. So we have TR is then equal to, our first temperature was 520, right? Is that what that was? 520. So we have 520 C, but we need to add 273 because we need to change it to Kelvin, right? Because our critical temperature is in Kelvin. Divided by our critical temperature, which is 647.3 K, right? And that is equal to, let me grab the calculator really fast. So we have 520 plus 273 divided by 647.3. And you get 1.22. 1.22. We'll just call it 1.22. Is everybody following so far? This right here is like easy points on the exam. This is exactly what you're going to have to do. Very, very simple. And then we have to do PC and P. So our actual pressure that they gave us was 20 megapascals. 20 megapascals is 20,000 kilopascals, which if you divide that by 100, I always have to do it the other way. So, but I'm pretty sure it's let's see, 20,000 divided by 100. Yeah, so it's 200 bar. So then we have 200 bar divided by 220.9 bar. And that gets us, do ahead and divide this by 220.9. 0.905. So 0.905. I'll rename these steps after we finish. But essentially it's gather the information about the fluid you're using or the gas. Step 2 was find reduced pressure and reduced temperature. So let's head back here. So they have, they did our, so right here is what we did. So 0.91, they just rounded up, but essentially this is what we found, right? They have 1.23 and 0.91, which are the same thing we got as without the rounding up thing. But yes, I'm just going to keep using our values. So then what we have to do is we have to go find the z value. So that's the next part. So let me go back to that chart. So this is you can use either one, the one from the chapter or from here, but this one from here is like more specialized. It like looks better to draw things, the bigger target. Let me see what this one is. Index. Okay, so this is probably the one we're gonna use then. Maybe actually we can't. No, we can't because ours is less. So really quickly, our pressure or our reduced pressure is 0.905. So we're gonna call it right here. So I'm gonna go ahead and do that. So it's like right on this, although I'm not going to be able to do this very effectively, but you guys are just going to have to use your imaginations. But I might just call it right at 0.9, right? And then I'll slide just a little bit over. So 0.9 is what we're driving up, right? We've reached our reduced pressure on 0.9. We now have to go up and find our reduced temperature of 1.22, I think, or 1.21 is the one we got. Or 1.22, okay. So 1.22. So let's find 1.2. So 1.2 is right here. So that means you can imagine that 1.22 is like a little slice sort of like right here, right? So we need to go up where that matches. So slide all the way up. To this point. And then if we draw a straight line over, which I know this won't be very straight, but although I seem to be doing an okay job. You end up with this. So our z value appears to be 0.88 or 0.89. Let's see what the actual solution got. There says 0.83. So we were a little off of that. I wonder why. Let me go look. Oh, I thought that was one more up. Oh, okay. Never mind. So we are right. I thought that we were right at 0.9. Apologies. So we are. So this would be 1, 2, 3, 4. So we're essentially at 0.84 for our numbers because theirs were different. So the thing is, once again, like using any table like this for like your fluids class or whatever, there is going to be some error in how you read this, right? It's used for a quick and semi-accurate calculation. It's not meant for, if you have better options, use those. But I'm going to say we're going to call this one at 0.84 because that's what it looks like to me. This 0.84. All right. So 0.84 is what we're calling our z value. So I'm going to go add that in here. And then z is equal to 0.84. So z is equal to 0.84 has been added in. So we can go back here. And so now that we have our 0.84 z value, you can then use z is equal to p little v RT. And the specific volume can be determined at the first state, right? Because remember, it's p times little v RT. And you can solve everything around. And they're going to do it right here. You can solve it all around, and you can find what your specific volume is. So they moved specific volume to one side, and they solve for it. So z times R times T1 over P1, and you get 0.83 times R T1. And then remember, because we want it per mass, we have to divide by the molecular mass of water, which is 18, which is why I grabbed it at the very beginning. And so this right here is the units check. So 0.83 has no units because it's z is the compressibility factor, no units. All right. And then you have 8,314, which is 8.314, but this one's expanded outward. So I think they did that was because it's a units check again. I think it was because of the units, not newtons. And so when you do this, you divide these two, you get rid of the kilomoles, in the kilojoule or the kilograms remain, right? And then down here, you do 20. This is 793 degrees Kelvin. Pretty straightforward, the temperature. And then this right here, the pressure. So they put this one in kilopascals, and so this right here is in kilopascals because 1 kilopascal, or no, this is in pascals. It appears so. So this is in pascals because this is a, no, this might be, I think this is kilopascals because 20 times 10 to this, I'm pretty sure it is in kilopascals actually. Let me look at that just to be sure. I wish I had a better calculator here. Oh man, so 20, let me see, 20,000 times 1,000. Okay, yeah, so this is in pascals. So it's a Newton per meter squared. A kilopascal is a kilonewton per meter squared. So this is in pascals, it appears. And so they put it in pascals, it looks like, to do this, to get rid of these, to get rid of the meters and the newtons over here. And then if you mess with all these units and multiply in by the right things, you end up with this as an answer, which is 0.0152 meters cubed per kilogram. So that is the specific volume at state 1, right? And so since we know that that's the specific volume at state 1, I'm pretty sure it ends up, yeah, it's the same thing. So, so we know that specific volume of state 1 is the same at state 2. So we finished the first part right here, which is, I'm going to go ahead and write that as we finish the first part, which is, so step 3, and this is little v. So I'm going to write the real equation. So z is equal to p v over rt, right? And then you end up with v is equal to z times rt over p, right? Because remember, z is just I like to separate ones that are just simple multipliers. So it's just z is like just a multiplier factor. And then once you get that, you end up with 0.0152 meters cubed per kilogram. So let's drag that across. So now that we know that, I'm pretty sure that is one answer, but we'll see if that's how they do it. Yeah, so we have found the first answer here, which is 0.0152. Okay. Let me see. Then we have to find the pressure at the final state. So that is our next problem, is that we have to find the pressure. And so it says, let's move on to that. It says, since both mass and volume remain constant, the water vapor cools at constant specific volume, and thus at constant Vr prime. Pseudo-reduced specific volume, I think, is what they're calling it. Using the value for specific volume determined in part A, the constant Vr prime value is the following. It is Vr prime is equal to V PC RT R over TC, or V times PC over R TC. And when you plug all of those numbers in, you get a constant value out, which is this. And what you're going to do with that number is you're then going to go to the table, right, and work backward. So what they're doing here is kind of clever. They're going to the table and working backward. So we have found that VR is that, which is pseudo-reduced specific volume, right? So for stage 3, I'll go ahead and write this, or step 3. So one of our answers is found. The next one here, step 4, is we used, so really quickly, this question is unique in a way that you don't use this stuff very often, this pseudo-reduced specific volume. So I wouldn't get too hung up on that. The part that I want you to really focus on is these first 3 steps. this is what you'll really be using it for the most part. This is probably the first question I've ever seen where we use pseudo reduced specific volume. So if you understood what I was doing for the first steps, that's kind of where I want you to be. But the rest of it is not that bad either. So V R prime is equal to V PC over R TC. Okay. And then when you plug in all of that again into this very long equation, you get 1.12 as a VR prime. And by getting a VR prime, we can use that in the table. But what we need in the table as well is we need the reduced pressure or the reduced temperature of stage 2, because remember stage 2 had lower temperature. So our second stage, I think, was 400 degrees C, if I recall. So it's 400 plus 273 divided by our critical temperature, which is the same. It's 647.3, and they get 1.04. So like I said, what they're doing here is a little bit clever. They found pseudo reduced specific volume, and now they're going to use TR as our secondary locator on the chart, and then they're going to combine the VR and the TR, and they're going to see where those cross, and then they're going to scroll down the table to find PR. And then once they find reduced pressure 2, they can find pressure 1 because they already know the critical pressure. So that's how they're doing this. So it's a backward step. We went forward here to find the specific volume. Then from step 4, we're going backward, more or less. All right, so we have TR2 and VR2. So really quickly, let me go back to the table here and show you. So our values were 1.12 for VR, and TR2 was 1.04. So let's go ahead and draw 1.04. So right here is 1.04, so it's going to be right like here, right, you would say? And this is our TR value, right? So right here, it's right on the border of 1.05, right? And then we need to find where it meets with these values, the sideways swooping ones here, which are the volume ones. So let me go back to these. It says we have 1.12 is our other one. So let's go find 1.12. You would assume is like somewhere like in here. So we go up, 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 and we find it right here. And then we go draw a straight line down. Once again, straight line. You're going to have to assume, use your imagination, that's a straight line. And you end up right here, which I would say is like 0.67 or 0.68, something like that. I don't know what they got. I probably said it already, but see what they got. They got 0.69, so we're right there with them, right? So 0.69 is what they found using the table like I just did. So I found where reduced temperature meet for stage 2, and I found where pseudo-reduced volume mix on here. And pseudo-reduced volume are these lines, the dashed ones going this way, and the solid lines going this from right to left are the reduced temperature lines. And I found where they met and went down here to 0.67 or 0.68, whatever. It's probably more 0.68 if I'm honest. But there it is. So now we go back to here. And so then now that we have our reduced pressure of 2, you can just redo the equation of this. It's PR is equal to P over PC, right? And since critical pressure is the same for everything, and we know our reduced pressure over here for state 2, you can just solve around and you'll find your pressure for state 2, your actual pressure. So let me go into the solution, and then you have P using chart P R2 is equal to 0.68. And then step 5, the last part, which is step 5, you have the following. You do P R2 is equal to P over PC, which if you then manipulate that, you end up with P 2 is equal to PC times PR2. And if you then do that, remember some of these might be in different units, although it actually doesn't matter because you just change the critical pressure, which is all the way at the front here, which is 220.9 bar, which if you change that, it is 22.09 megapascals. And so you put that in there and you multiply by 0.69. So, or our value of 0.68, which I will do in front of us. Let me see, calculator. So, 22.09 times 0.68. And you end up with 15.02. This is MPa. So 15.02 MPa. So that right there is the pressure at state 2. Now, really quickly before we get out of here, we're going to hold on really fast to these values. So this pressure right here, 15, so essentially 15. We'll just call it 15. And then let's go look at our other one, which was this specific volume, okay? Which is 0.0152. So let's hold on to that, and then let's go to the tables. So we're going to the, not this table now, we're going to the water tables, okay? So, and we have to go to the superheated water tables because they already told us it's superheated, but you could figure that out for yourself by using the tables here. You could do it. Oh, this is propane. We're not even in the right one yet. All right, 134A, and a little further up. So, they told us it was superheated, which I don't remember what our value, wasn't it 20 megapascals was our first value? Yeah, 20 MPa. So if you go to 20 megapascals, which is right here at 200 bar, and you go across here to 365.8, that is the temperature that we have to be for it to be boiling. We are way higher than that. We're at 520. So we are superheated for sure. But remember, this is for gases, so that's you. It's kind of assumed that it's going to be superheated because they're treating vapor as like a gas. Okay, so if it was water, obviously this probably wouldn't work very well. So now what we have to do is we have to go find 20 megapascals, 520, and then find the specific volume. So 20, that's 2 megapascals. Let's find 20. 14, 20 megapascals, 520. The specific volume is 0.01551, and our value is 0.0152. So these are pretty dead on, right? Now, obviously, this way was faster, but the reason why you would do this other way is because if there are no tables for, let's say, you get nitrogen as a gas, you will not be able to use any tables because we don't have tables for nitrogen. So you will have to use this way to find those things for nitrogen. But for water, this was just showing you that the comparison is accurate, right? So we have 0.01551, we got 0.0152 as an answer, which is pretty dead on. Then let's check the pressure one. So the pressure one, we need to find a temperature of 400 Celsius. So 400 Celsius, and we have to find a value that matches our specific volume in the pressure line. So this is another way to read the tables. So 0.0152 and 400 C. So, I mean, I already know what the answer is, obviously, because we're doing it. But essentially, if we go to 400 C, and we go over here, you'll find that 14 megapascals is 0.01722. And then if you go to 400 here, At 16, it is 0.014. So what that means is that we are looking for a specific volume on this chart of 0.0152 at a different pressure. And as you can see, we are in between 16 and 14, right? There's no table for 15. And since there's no table for 15, we can't actually read over. But I think you guys, being intelligent and understanding, would know that if we're looking at this temperature line and we get 0.01426 for 16 megapascals, and we look at the same temperature line up here at 14, you get 0.01722. Our answer is in between those two. And what is in between 14 and 16? It's 15, right? And our pressure, that means that there is a missing table entry. If there was a 15 megapascal window, or like this, it would read our value at 400 degrees. And it would read, so our pressure is 15.02 megapascals, essentially. And so it matches up, right? It matches up with reality of what the tables show. So that means that this process was done right. And like I said, you will only use this process if like the gas that you have is something you cannot look in the tables. For water, I would never do this, because this would be really dumb, right? To do all these steps for water. But if you get argon, nitrogen, oxygen, anything like that, you will have to do something like this. But like I said, the main steps that I want you to know are these first ones right here. These are the main ones. The ones down here are good to know, because questions might try to fool you by having you go backwards and use the table backwards. But for the most part, most questions that get asked in this class about this subject are this. It's finding TC, it's TC and PC, finding the reduced pressure and the reduced temperature, and then finding whatever value we told you. And then the usual conceptual question is, based on your Z value, is this gas ideal or not? Right? And since our value of Z was 0.84, you would say that Z is not equal to 1 or very close to 1, so therefore it is not ideal. That is what you would say. If this value were closer to 1, it would be ideal, but this is fairly far off of ideal. And so you would say that. You would say this is not ideal due to that reason. But that is a conceptual question that you should probably expect on the first exam. I would be very shocked if we didn't include it. So make sure you hold on to that. But I'm going to go ahead and take attendance, and then you guys are free to go. Really quickly, though, before we roll out of here, we are almost done. Let me go ahead and shut the recording off.